Again, it's my pleasure to introduce the next speaker, Dr. Satish Gupta. Many of you know, some of you have probably heard the presentation, similar to what he's going to make, but has done for us some very interesting work in looking at where sediment is coming from, measuring it. It relates to one of the speakers this morning, and it does tie directly into the comment of Dr. Trimble regarding Lake Pepin.
Thank you very much, Willis. It's great to be here. I think after the last couple months of my name showing up in the Star and Tribune, I'm probably pretty famous in a wrong way. It affected my family, my kids a little more than affected me. I'm used to it. In 1994 and 5, when Willis was head of that committee looking at this MNRAP, I got the same kind of mud thrown at me. And so I think I was thrown out of the MPCA building at one time too. So I think I'm pretty well used to it. What I'm going to do is, I think there were beautiful and really nice presentations this morning, and also Stan Trimble's presentation. Actually, Gary Fox, Stan Trimble, and there were another 15, 20 people. We had a symposium about 5 years ago at the American Society of Agronomy that I organized, and so it's more like a gathering again for the same kind of issues that you guys are interested in. So the title is Sediments in the Minnesota River and Lake Pepin, Causes and Effects. First, I'm going to give you guys the conclusion of my presentation, but please don't take that conclusion as a farmer and go and do every kind of damage to your land, okay? If you guys can do the conservation tillage, conservation practices, they're important, there's your land, you're going to pass it on to your kids. I am just going to give you my scientific opinion of the problem that I've been looking at it. So first thing is, there are too many inconsistencies between different studies as well as the historical records, and we need to resolve those. The second is, I'm not sure at this stage, after listening to many people in the state as well as my own work, whether we have the diagnosis of the problem right. It could be I am wrong too, but I think we need to figure it out, what is the diagnosis of the problem. If you guys remember, within last month, there was a report that came out that said we have spent $1 billion over 10 years and we still have not achieved it. The question somebody need to ask, do we need more practices, or is the problem is it's still not rightly diagnosed? So I think we're at that same phase that I'm not sure we have diagnosed the problem right. And the third is, I think to overcome that problem, we need to do some more research. Not I'm asking for more money from the agencies or the Corn and Soybean Council, because I can retire in a few years. Okay? Drew showed you this, I'm not sure which button is which. Yeah, okay. This is Dr. Angstron's data from Lake Pepin. It shows the rate at which the sediments are coming over there. This is 1.6 centimeter per year in the lake. And if you go back 1500 to 1830, it's about 0.2 centimeter. And then 1830, it all of a sudden jumped to about 3 or 4 centimeter, 0.4 centimeter. And it's been continuously kind of increasing. And their argument is that in 1830, settlers came to this area and cultivation was done, and that's the reason for this increase in 1830. And then 1910 or so, where the tile drainage, the system was installed over there or started to install, and that's why we have the higher rates of sedimentation in Lake Pepin. And I disagree with them on this, and I'll show you in a minute. Now I'm going to recap what Drew mentioned, and we have used the LiDAR, and we looked at the amount of sediment coming. In 1994, when I suggested to MPCA, please have a look at the bank erosion. They wanted to do no-till in every piece of the land in the basin, and they thought they can reduce the sediment by 40% in Minnesota River. And we would have come back to this point because we didn't, if we had not looked at the bank erosion. Now everybody agrees the bank erosion is a big problem. So we're finding about 62 to 78% of the sediments that are coming at the mouth of the Blue Earth River and the Lasur River, they are from banks of the rivers in this basin. Now, if you think about it, take a clod, and this is the extreme case I'm going to show you. You just take a clod and put it in about 1 centimeter of water, and in 20 minutes, see what happens to this clod. What happened? It just kind of collapsed. Now, this is the extreme case. I've done it for the other ones too. It's a little more time, but they disintegrate. That means the strength of the soil is not there when it comes in contact with the water. So there are two elements which are important, the strength of the soil and the water, as Gary mentioned this morning. Okay? So where does the water come from? We don't have any irrigation in this basin. It's mostly precept. And the strength of the soils are developed over millions of years. They don't change over 150 years when the settlers came over here. So there's something else going on over there. So banks are eroding, or they're slumping, as Drew showed over there this morning. And I mentioned about the seepage, and also Gary mentioned, this is the seepage during the winter time. The water is still moving at that depth, and it's just freezing as soon as it comes out. This is the bank that I showed yesterday to some of the people who were there. It's in Vernon Center. And this part, if you look over here, this is about 20 feet above this, and it just slumped. The owner of this place says she moved about 14 years ago and feels like the earth is sinking. So people, when they make that observation, their observation about the science of physics. We just got to figure out what it is that's causing it. This is the last year, March 2010. This is April 2010. These trees just came down, and you can see the seepage over there. And there is a seepage over here too. This is the bank we showed yesterday. This is ready to go. This was in a small grain over here. This is in the Blue Earth River. And that's going to be tons of soil. It has nothing to do with undercutting. This has just kind of slumped down about a foot or so. Somehow water is coming in the back over here. It's just kind of doesn't have enough strength and just taking it down. This is Kevin Papp's. I have not gone to his field, but look at the grass. This is also in the CRP. It has nothing to do with the cutting. It just kind of slumped. This is 2005. There's a seepage spot over here. This part of the bank went into the river, and this is the collateral damage. So we were interested in 2005. We thought it was seepage, and we want to check it out and see what happened. So Nate Bartholomew was a PhD student. This is in Eagle Lake Park over there, and we put a little bit of this berm area, put some tensiometer. We had a series of piezometers, and we just kind of flooded that area. And then we just made a movie. So you're going to see, this is about 15-20 minute movie, but I'm going to show you the last 1 minute. We thought the water was coming over here, so we had kind of sprayed with this paint over here. And we're making a measurement. This is about 7 feet deep over here, and yesterday Gary was showing some tunneling, and we saw the same tunneling right here when we were adding the water. And you'll see that about 2 tons of the soil in a 10-15 minutes just came. And there's an area on this side, there are trees, and there's an area on this side that's trees, and those are not slumping. It's only in the middle that was slumping. So one of the reason is, I think there are layers underneath. Somehow underground water is converging to this site over here, and that's why it has been slumping over there. So when you add the water, the soil does not have enough strength over there. Water pressure is much higher, and that is forcing the soil to have a rotational failure like you saw. So the strength of the soil is very important. The availability of the water is very important. And the strength of the soil is, of course, you can't change. Availability of the water is either from the precip or from the river water. That's another bank that we saw yesterday. Now, I've been monitoring this bank from 2001. You can see in this case, river water went into the soil, seepage the other way, and it was holding the soil over there. When the river water went down, there was not enough strength, and it just slumped like Gary mentioned. So next time it will be taken out. Now this soil, it's in the middle of the bank. Drew had shown this bank over here. It has nothing to do with the undercutting. There are some places probably undercutting is happening, but most of these banks are slumping from the top or in the middle because of the seepage process. And it's a very difficult process. How do you manage it? Last year, Will Purvis showed us this bank. This is again by the big bank that I showed you that lady says is sinking. This is the debris that you see at the bottom over here. We came back. This is May 27th. June 28th, this is from the top. Where I'm standing taking the picture, the owner of that place says she could have walked over here to the tip 14 years ago. Now this is on the same day, this is the bottom, how it looks like. In a month, it's gone. Okay? There was some rain, There was some windy conditions, but the river water never touches this bank. This is on Maple River. Last year, you guys had about 10 inches of rain in the fall. And this is a peninsula over here. This is a $2.1 million bridge over here they constructed. And this is the channel, original channel length, channels where it was flowing in the blue color. And all this soil that you see on the black is taken out. So the road was taken out, and the farmers were laughing that we got a $2.5 million fancy fishing pier. Okay? But a lot of soil went down there. This is a 1938 picture, and this is the position of the river in 2009. 20 meter is about 360 feet. That's a lot of movement. This was an oxbow over here, river cut over here directly, and it's kind of stranded now, and so it's cutting into the banks. And part of the reason is flooding. Okay, flooding could be two reasons. One is we got too much rainfall. The other, you got to keep in mind, in Blue Earth County, all the rivers are flowing to the north, just like the Red River is flowing to the north. So if you got ice jam near the end mouth of the river, then you're going to have backup of the water over there, and that's going to cause some flooding, and that's going to have water moving through that field. So I'm going to give you a little section by section some findings, and so you can understand what I'm talking about. Banks are sloughing up from the top and has nothing to do with the river levels. This sloughing appears to be due to seepage. Bank sloughing is also occurring due to catastrophic events and channel migration. Agriculture is also contributing some sediment through the surface inlet, and I think for many of you who are farmers, try to figure out a way to take the surface inlet out by putting the rock inlet or some other mechanism. And the important factors in this sediment transport are coming from the bank is the soil strength and availability of the water. So now if you look back and you say it's soil strength, soil has not changed, water availability is from the precept, that means these rivers must be slumping even before the settlers came here. So you start looking at the history, and this gentleman, Fanshawe, 1847, he was a well-known geologist. He comes to Mankato from St. Paul and looks at the Blue Earth River on September 22nd, 1835. And he says this was a bold stream about 80 yards wide, loaded with a mud of a bluish color, evidently the cause of St. Peter being so turbid. St. Peter was the previous name for Minnesota. We don't have muddy rivers in September, October, November. Okay, the reason was we had a big rain event that he mentioned in his book. And then he says the Blue Earth River appears to form about half the volume of St. Peter and is a very rapid stream. Exactly the same thing that the USGS found in 1994. There are a whole series of historical records. I have compiled it, and this is another one. This gentleman has written a book. Evan Jones has written a book, The Minnesota, the Forgotten River. Some traveler comes from the St. Croix River to the Minnesota River up here, and he writes in his diary, the Minnesota River, he wrote in 1856, is a dirty little creek. You know, 1856, we didn't have sewage going in the rivers, we had a mud. And creek means it's a smaller size than the St. Croix River. In 1904 and 1905, USGS has taken some measurements in Mankato, and they were measuring ordinarily the turbidity is 10 to 40 milligram per liter. It's a different method. But in that year, 4 and 5, it was as high as about 400 milligrams per liter, and they said they can find as high as about 600 to 800 milligrams per liter. That's a lot of sediment coming in 1904 and 1905. Now, many of us have seen this picture over there, and I have used it myself. This is by MPCA. Some gentleman, David Morrison, took that. And you look at this, and you're in the city, people, you're horrified where the hell this mud is coming from. You know, you like to take care of that. Now, you go back, 1937-38 was the first time any aerial pictures were taken in the state of Minnesota. In September, I know there's too much light, you can't see any difference, but there's a little bit more cloudiness in 1938 than this is St. Croix, this is the Mississippi River. October you don't find it, June again you find it here, and July you find it. September, October, November our rivers are clean, whereas other months, early spring, our rivers are not, and that's what you're seeing, what he saw in 2004 or so. This is Department of Conservation picture from the Historical Society. 1960, May 1960, before plastic tile line came in Minnesota. And it looks as bad as it's right now. Now let's go on to Pike Island. Fort Snelling is around here. This is the Mississippi River. This is the Minnesota River. And June 30th, 1937, you can see some difference. And you can see a difference in 1940, and you can see in 1956. Now look at the Blue Earth River, 1938. This is the Minnesota River coming, and this is the Minnesota Blue Earth coming. It's the same. You have the Blue Earth contributing to Minnesota turbidity that you see over here. This is the Waterman River coming to the Blue Earth River. Waterman is cleaner than the Blue Earth River. So the finding for this section is the Minnesota River and its tributaries have been muddy or turbid since before pre-settlement time. We don't know how muddy they were compared to this time, but they were muddy. Now I'm going to go back to this diagram that Dr. Engstrand has put together, and he says this is the start of the cultivation, that's why this rate increased. Population of the state of Minnesota in 1850 was 6,077. Most of these people live in St. Paul, Minneapolis, Stillwater. Okay? There were hardly any people in the Minnesota River Basin at that time. Most of the early agriculture was very primitive. You guys are lucky, you guys got fancy combines and tractors. They had a moldboard plow which was made out of wood with a metal tip. And sometimes they'll put a scrap metal on the side, and then they'll take a paddle, and every so often they'll stop and scrape the soil off because it's a sticky soil. They could have not done deep cultivation in the soil. And then we have, this land is very flat. You go outside, just like Stan mentioned, in Coon Creek, southeast Minnesota and Wisconsin, you need slopes to get the soil out. Our land is very flat except for the surface inlets, and we got to take care of that thing. And then at that time, it was a just kind of sustainable, primitive agriculture. They just needed enough food for themselves and the family. So they did not drain very many lands. Mostly they have is a rotation crop. They'll have a small grains. Wheat was a big king. We had a lot of wild hay growing over there. There was some flax and there was some corn too. But mostly it was applying manure for the nutrients and so on. So that could have not caused this increase that Dr. Engstrand is saying. So there's some other reasons. Now the reason they have been kind of saying is that row crop. They say we have increased the area under row crop, which is corn and soybean, and that's what's causing it. And that's based on this paper that Dr. Mulla and his student has put together. And what it's doing is, it's looking at how much of the sediment is coming to Lake Pepin from the Minnesota River and the upper Mississippi and the St. Croix River. And they're just regressing that versus the area under row crop over time. So this says from the Minnesota River, every hectare of row crop contributed 0.234 tons of soil to Lake Pepin. And similarly, for the upper Mississippi, it's 0.188 for every hectare. Now when you go to St. Croix River, you say we are going to have for every hectare of alfalfa land, we're contributing 0.065, and for every corn and soybean, we are contributing 0.037. If you are an agriculturist, it should not make sense to you because row crop is more erosive than alfalfa, and this says alfalfa is giving 2 times more sediment to Lake Pepin than the row crop. So you cannot use regression type of approach, although Dr. Mulla has mentioned, well, we should not use cause and effect. But that's what the basis of Dr. Engstrand's proposal is, that it's a row crop that has increased and that's causing it. Let's go on to the second point he has made. He says it's a drainage, and the drainage did not start in this area. It was limited initially. How many of you guys know Wally Nelson? I had to call him to find out what he did. He remembers from when he was a young kid on his farm in Redwood County. And most of the initial drainage was limited only to the depressional area. You'll put a surface inlet and get the water out. And even when there is a storm, they had to go back and clean up the surface inlet from the cobs and so on right when it's raining. The water would stand over there. And so 1910 to 1925 and 30, 20% of the land benefited from the drainage. And then in 1930 came the drought and the depression. Most people lost their farm. They didn't have enough money to put any drainage over there. And then 1940, many of you guys went to World War II, and there were not enough men to do the work over here. And they were also growing, most of the crop were still in 3 to 5 year rotations, corn with oats, meadow and meadow. And that would have limited erosion compared to if you just continuous corn like we have right now, or a corn soybean rotation. And then 1950, the drainage picked up. It was still clay tile and the cement tiles. Some of those cement tiles would degrade over time. Clay tiles, if you didn't put them close enough, the roots would go in there, the soil would go in there and it would block it. So then came in 1970 the plastic tile line. The Lamberton station, they had the tile line put in there, 15,000 feet of the tile line in 1971. The gentleman who put it in there, I asked him, why didn't you use plastic? They put a clay tile line. And he said, at that time we were not sure if the plastic tile line can withstand the frost pressure of the soil. So most of the tile line came after 1970s and 75s and so on. So now we talked about the lake sediments in Lake Pepin, and Drew had talked about the sediment production. We know it's coming mainly from the river banks, and there is, of course, there is a surface inlet too. But we have not talked about this part, and that's where my hypothesis comes. We think we have changed this transport process. So if you go back, if this is the Minnesota River Basin and this is Lake Pepin, we used to have a lot more wetlands than we have now. We have done a lot more ditching too. We have tile lines taking the water out. The Minnesota River between Mankato and Lake Pepin was a lot more crooked. How many of you guys know the Lake Pepin started in St. Paul 11,000 years ago? Anybody? One or two? Okay, this started in St. Paul, it's filling up, and now the headwaters of Lake Pepin are in Red Wing. So this was a crooked river. Sediments are going to definitely stay in there, some of those sediments. We have a lot more precip, and now we also have a lot more impervious surfaces. Many houses, the Mall of America and the airport. So you got a lot more water going, storm water going over there, and there's also a little delta that's moving down in Lake Pepin, and that has some consequences when you take measurements. And of course, we also have a couple of dams, not 3 dams, there are only 2 dams in this stretch over there. How many of you guys seen this picture in Star and Tribune? Lots of you guys, right? This is the Pike Island, this is the Mississippi River, this is the Minnesota River, dirty. But nobody went back and took that 1937 picture I have. This is the Mississippi River, this is the Minnesota River. You can't see the color differences, but you can see it's still muddy. Now, one part of the reason, another thing you want to maybe look at it, why didn't the Minnesota River go directly here? How many of you guys been on the Pike Island? It's a sandbar, it's a large sandbar. And part of the reason probably it developed is there's a 100-foot drop from St. Anthony Falls to Fort Snelling, 25 miles, there is a 100-foot drop, so there's a 4-foot drop for every mile. Between Mankato and Fort Snelling on the Minnesota River, it's a 6-inch drop. So velocity is not very high, this water is coming very fast, it's pushing it. So if you go in the Army Corps of Engineers record, this mouth of the Minnesota River was blocked every year from 1893 to 1943. There will be a sandbar, only 18 inches of water would flow over it. Behind there is a 6-foot deep channel to Shakopee. So here is some of those records. Congress authorized the Army Corps of Engineers to dredge the Minnesota River. From 1893 to 1943, a sandbar formed every spring, leaving about 18 inches of water at the entrance and 6-foot deep channel to 24 miles. So now we have been dredging it every year. What do you think what we do when we dredge it? We're letting the water out. Water would have gone out anyway, but we're letting the sediments out too. World War II, Cargill got a contract from the US Navy to build ocean-going oil tankers and towboats. And where do they put it? On the Minnesota River at Savage. And as part of the contract, Navy was supposed to dredge 9-foot channel. So that's one of the boats. This is going to New Orleans in the ocean. And here is another one. Now you think this boat has to go, you got to dredge the channel over there. And when you dredge it, you're letting the sediment out. And now we got a black dog 8 or 7 power plant over there, and we have a Richardson Oil Company, and we have Cargill grain elevator. So we have been taking the barges, and we have to do this dredging every year. So Mankato, you guys know we have built the levees, right? There's a levee in Mankato, levee at Henderson, and levee on the Blue Earth River. What does a levee do? It's forcing the water and sediment to stay in that channel. Why is the Army Corps of Engineers are busting the levee on the Mississippi River? Because to get the water out, so there is no flooding in downstream locations. So what was happening before? This is a picture, 1881 floods in Mankato. This water never got to St. Paul, right? 1908, this water never got to St. Paul. 1916, 1951, 1965, right? And that's when the levees started being constructed over there and try to keep the water and the sediment down in there. So finding from this is that dredging opened up the Minnesota River to downstream transport of sediment. Levees eliminated the floodplain interactions and are forcing water and sediment to downstream locations, including the Minnesota River at Jordan and Lake Pepin. And I'm going to talk about the Jordan because you guys have heard it in the newspaper. Okay, there have been a lot of opinion pages going in the newspaper. People have been saying we got more flow because of tile line. The rivers are wider because of the tile line. And the river's flow is non-linear. And the flow at Jordan has doubled. And I'm going to address some of these. And some of that is coming from Dr. Shardler's. Please, if you are in the audience or if you're friends of them, this is not criticizing personally. We are talking about their science, and we'll need to look at this thing to figure it out what we need to do. So Dr. Shardler has heard me before on this thing. He gave a presentation last fall, and he said as the rainfall increases, flow should increase, and that's true. But then he says the ratio of flow to rainfall should be constant over time, and that's not the right assumption. Okay? So what we call is runoff depth, the water in the river divided by the precip is runoff ratio. Now I'm going to do a little simple experiment in the graphics. You'll see what I'm talking about. Most of you guys know when the soil is wet, most of the water runs off from the surface. When the soil is dry, there is some water that goes through the soil. So the runoff ratio in the wet soil is more than runoff ratio in the dry soil. So now this is my rate at which water is going into the soil, and this is the time, and this is how most of the infiltration curves look like. This area under this curve is runoff, the area under this curve is what water gone into the soil. So now let's say rain stopped after 40 minutes. This is going to be the runoff, and this is what went into the soil. Let's say it went to 80, now runoff is increasing proportionally than the infiltration, right? This is for 120, we got a lot more runoff compared to the increase that we got in infiltration. So if you plot this runoff coefficient, the runoff ratio, as the precip increases, we have increase in the runoff ratio. So runoff ratio should not be constant. So runoff and runoff coefficient increase with increase in precip. If you are in NRCS or agency people, you have used this curve number method, which is a relationship between the runoff and the precip depending upon the soil conditions. So let's take the runoff volume as a function of precip. We have a group number A, which is sandy soil, and group number D, which is a clay soil. So at any given precip level, there is more runoff from the group number D, which are clay type of soil, than from the sandy soil. Makes sense. If you take the runoff ratios are higher from the clay soil than from the sandy soils. This is just for group number D, and we're going to look at if the soil is wet and dry. So green is the wet condition and pink is the dry condition, and in between the blue color. And again, at a given precip level, there is more runoff from the wet soil than from the dry soil, and if you take a ratio, there is higher ratio from the wet soil than from the dry soil. So there is a greater effect of precip on runoff and runoff coefficient from slowly permeable clay than highly permeable sandy soils. As the wetness increases, proportion of precip goes into the runoff, increases with increase, and it's an increase in non-linear. So now if you go back in the literature, and this gentleman comes from the neighborhood where Gary came from in Oklahoma, he's done some work where he has plotted the stream flow versus the annual precip for watersheds in Oklahoma, Kansas, and Nebraska. Look at this relationship. Is it a linear or non-linear? It's a non-linear. As the precip increases, you have more and more water going into the river. And Mark Seeley just mentioned this morning, we have had wet climate over here. So what we did was, there are 84 Huck 8 level watersheds in the state of Minnesota. So we took, where you see this blue dot, those are the watersheds that we took, and we looked at the same relationship. So here is the flow in the rivers, and here is the relationship with the precip that we have got, and this is a record going back to 1930s to 2008 or 9. So you can see this is what the gentleman from Oklahoma came up with, and these are Minnesota watersheds. Okay, we get a lot more flow at this precip level in Minnesota than they get in Oklahoma, because we have a shorter season and we don't lose very much water in evapotranspiration, and that water goes in the river. If we are here, Minnesota River is here, and this is up north near Rainy River and so on. Now if we plot over here, if we get Minnesota gets 1200 millimeter, our runoff is going to go way up, because we don't have enough water leaving our landscape through the evapotranspiration. Oh, this is, Mark showed similar graph, which is 1895. This is the amount of precip that we have got in this area. You can see we have got, these are the 5-year average moving line over there, and from here you can see there has been an increase in precip. Now if I divide, the flow record is available in the USGS gauges starting around 1938 or so, and let me divide this one period and that's another period. And let's assume we have some tile drainage here, but a lot more tile drainage here, right? So if you compare those two, it should show up something. So in here we have the flow and the precip level, right? This yellow line is a period before 1975, and this aqua line is after 1975. So there is slight increase in here, right? Now this point is 1993. We never got that kind of precip in the period before 1975. Part of the reason this is going up is this. If you take precip greater than 1000 millimeter, the total points for the period prior to 1975 is 140, and after 1975 is 165. But there were only 2 years when this value is greater than 1000 millimeter, whereas in here it's 8 points. So those heavy precip values are pulling that aqua line up there. Now the other thing you want to think about is, this is the Minnesota River basin for these 4 watersheds. But did this happen in other parts of Minnesota? And lo and behold, this happened in southeast Minnesota too. So if somebody thinks this is because of tile line, then what is this because of? Okay, that is because of precip. So now you can also look at the upper Mississippi River, Elk River, and the sandy soils. You find the same kind of relationship. And if you run the statistics, these relationships are not different. So at any given precip value, you have almost the same kind of flow now when we have more tile drainage than you have before. Okay, the quantity has not changed, but that water is still flowing through the ditches. So something is probably happening. And what's happening is we have changed the timing probably. Okay? So in here, now you guys heard about the Jordan. This is the flow after 1975, and this is before, and the flow at Jordan has doubled. Now you guys just saw, and I showed you that precip has some effect. The other effect you got to think about is, when the floods were happening in Mankato, that water never got for this yellow line. If that water you add, 90-60 point is someplace around here, that would have jumped up way up there. So we have changed the channel. we have put the levees, we have dredged the material out of the channel. Increased precip will lead to non-increased linear increase in runoff and river flows for a given annual precip. There is no difference in river flows for the period 1975 and prior and after 76. This is only for Huck 8 level watershed. If you go on a smaller watershed, you might find it, but the records are not there to figure it out. This would suggest the tile line effect or the cropping system effects is not affecting the quantity of water that's leaving the watershed. However, tiling effect could be on the timing of the flow and also a smaller watershed. It could be on a weekly basis, daily basis. And the flows in the Minnesota River at Jordan are higher both due to increased precip in the area as well as presence of levees upstream. Now the second point Dr. Shortler made was in his presentation, and Mark made it this morning too, that if you look at these differences between 1976 to 2009 and 1940 and 75, we'll find that there is a more precip coming in the month of August, September, October. Mark said September, October, and November probably. And then May and June and July there has been decrease or there is no change. And Dr. Shortler thinks if you plot this flow, this is the runoff ratio, it's increasing. And he thinks it because of evapotranspiration, because we substituted the grain crops with the soybeans and the ET has gone down, so there is more water coming into the channel. And that's not true too. Because what Mark said this morning was that we are recharging the soil at a different intensity. So this is the amount of available water as a function of the month. This is the winter time, January 1st, and you have some snow melt, there's some recharge increase in the water content of the soil, and then you plant some crop over here and it's all depletion, and then again start in August or so you start recharging that soil. What you have done is, instead of going at this slope, there might be a much increase, faster increase in that curve. But this point still comes over here, and when runoff occurs in the month of these months, it has some impact what happened in here. You cannot just take a month of May, June and July and relate it to the precip and ignore this part, because this what causes the runoff to happen, because soil has to be fully recharged before runoff is going to occur. So you cannot look in isolation whatever has happened. You can look at an annual basis because our system shut down. We have very little flow in the month of January, February and so on, and we start all over again. The other thing that you want to see is, this is from the water encyclopedia. This is the amount of water used by different crops. This is for southwestern United States. This is the Missouri Arkansas basin. Corn uses 1.44 to 1.99 feet of water. Okay? Look at the soybean and the beans. Beans is this over here, soybean is here. 1.66 to 2.81. This number in the parentheses is number of studies that they have compiled. 36 studies. These soybeans is replacing wheat, barley, oats and flax in the basin. This value is a little higher than even what these values are. So evapotranspiration has not changed the water quantity that's leaving the basin. Now I compiled some numbers. The closest I have come to is the South Dakota, southern Alberta, and if you look over here, soybeans are 1.31 and 1.37 feet compared to corn. These are within these values. Again, wheat is about same, and barley and flax and oats. So the water use has not changed between the crops by substituting soybean with something else. Climate, which is a precip, and the ET has a big footprint on the river flows. If you're northern Minnesota, you don't have much ET, the crops don't go in the field, they go in the lake, so water is more coming in the rivers than in southern Minnesota. For every 100 millimeter of the rainfall increase you get, you are going to get a lot more flow. And increased river flow does not appear to be due to the introduction of soybean in cropping system. Now let's look at this thing, some inconsistencies between their studies, my studies and everybody else's studies. Kiran Grant has just finished a study. She has published a paper, and also recently she did a study for MPCA. and she did it on the Lusur River, and she says she had a flow data for 2000 to 2006 and 2000 to 2010 that she compared, and in that paper she says the TSS load in recent years at the mouth of the Lusur River are only 1.3 to 3.4 times higher than the Holocene average, which is 11,000 years. First, I would not compare 6 years of data to thousands of years because you can still have blips in the thousands of years. But let's assume it's correct. And then she says this increase appears more modest than tenfold increase in sedimentation rate in Lake Pepin. Lusur and Blue Earth River are the most erosive basin in this basin. So think about Lusur is giving 4 to 5 times higher, and everything between here and Lake Pepin is as erosive as Lusur basin, then the Lake Pepin should be 5 times higher. Why is it 10 times higher? There must be another source of sediment. Either we have the legacy sediment in the flat valley, or we got sediment from southeast Minnesota above the mouth of Minnesota River, above the mouth of headwaters of Lake Pepin. Stan just mentioned that. When they were doing this 70-80% coming from the Minnesota River, they could not differentiate between the southeast Minnesota sediments and the Minnesota River basin sediments. We know there is a 12 to 20% slopes. We know Cannon River, Vermilion River, and all of those are muddy rivers. We don't know how much that contributed. Now, another thing you saw in the newspaper, that was given that 35% of the sediments coming right now from the fields and 65% from the banks. And then in 1940, 65% was coming from the fields and 35% coming from the banks. Now MPCA, they have never put this whole chart which came from Dr. Shartler's research in their TMDL document. They only mention 2007 and 1944, 40 years on. Now using the tracing technique, what they're finding is 1890 to 1940, it's greater than 100%. Physically, it's impossible. We don't know what the number is. Is it 102%, 110, 150, or 1000%? Now MPC had never put that thing, and I've talked to Sean about it, and their argument is these model estimates assume the upstream trapping of sediment has remained proportionally constant. What you find in here over time, historical field percentages greater than 100% suggests that current trapping efficiency may be greater than past rates. So they're saying there are more sediments staying in the basin than they're going to Lake Pepin. Now I just gave you an argument. Lusur River is 4 to 5 times higher, right? And if everything is, then it should be 4 to 5 times higher. So if these sediments staying, then the Lake Pepin would have been, the rate would have been more than 10 times, 15, 20 times. We know it's not possible because we had floods in Mankato, we had dredging, we are pushing more sediment down there, and there is a dam over there. But the dam gates open during the flood year, so sediment has to go down. So we got to figure it out. You cannot assume the efficiency, trapping efficiency is same in here than over here. According to my thinking, we saw this bench yesterday, and Gary mentioned that if you don't, but the only way you can do, or one of the ways you can do, is put a tile line at different depths. So if we did not have tile line before the people came over here, these banks must be slumping at higher intensity than they are doing right now. So this possibility that 100% is coming from the field when people are not around doesn't make sense to me. Now you can look at this picture, that's again me over here. You think this tree was not slumping before the people came here? So it doesn't make, there are a lot of inconsistencies between different databases. We need to resolve that. I'm going to come back to my conclusion. There are too many inconsistencies between different studies as well as with the historical record that we need to resolve it. That does not mean they are wrong. I could be wrong too, but we need to figure it out, okay? I think our diagnosis of the problem may not be right. That they think that the impairment is because of tile drainage. I do not believe it based on what I've looked at the analysis. And I suggest we do some more research before we legislate, regulate, or spend any money that we don't have. Okay? And I am not asking corn soybean councils to give me any more money. And these are the people who have helped me. There are many more, and the funding came from the corn soybean council. And I wanted to show this bank. This is on the Lasur River. Yesterday, the soil was so muddy we couldn't get there. But at one time, 1965, this bank slumped and blocked the Lasur River. Thank you very much.